Hi all, my name's Associate Professor David Geelan from Griffith University on the Gold Coast in Queensland, Australia. I'm making this video initially for my own students that I teach here at Griffith University, but I'm going to put it on open YouTube for anybody who might find it useful or interesting, so I hope you do. I wanted to talk a little bit about science, what science is, and the nature of science, but this is specifically in the context of for an audience of teachers. So for those teaching science to primary school students, secondary school students, or even at university, I hope this will be useful as just a quick backgrounder. It's not enormously deep, but hopefully it'll give you a bit of a sense of the philosophy of science, the nature of science, as it pertains to teaching science. So if someone asks, what is science? There are a number of possible approaches to answering that. And different people will come up with different answers, but I think there are at least 4 bits that make up an answer. So the first one is a set of methods and standards. Science is an approach to making judgments about knowledge. It's evidence-based. It requires usually experiments or inferences from evidence. So there are scientific ways of proceeding, of testing a knowledge claim, claiming to know something and then testing that with experiments until either the experiment shows that it's not correct or the experiment continues to support it. And we'll talk more about that concept. So one thing that science is a way of inquiring into the world, of coming to understand the world better. Having done a lot of that already as a human species, we have a big body of knowledge. So the second thing that science is a body of things that we already know. So we know something about our moon, for example, how far away it is from the Earth, how big it is in diameter, what the temperature is at the surface. We know that one side of it always faces the Earth and the other side always faces away. So this is a body of knowledge that we know in science, and we know a lot about a lot of things. There is this existing knowledge. Now, learning science is not just memorizing this body of knowledge. In fact, that's not all that useful for a couple of reasons. One, because it changes rapidly. I have written science textbooks for schools for a long time, and we started thinking that we knew about 10, 15 planets outside our solar system, and now we know about hundreds or possibly thousands of planets outside our solar system. So we had to keep updating the knowledge in the book as science advanced. There are similar things happening all over the place. And the other thing is that scientific knowledge is available online relatively easily to access. So there's not a lot of point in memorizing it, but some things it's helpful to know anyway, just because it saves you going and looking them up. But a lot of the things, it's much more about being able to use those standards of judgment to judge whether what somebody tells you on the internet is true. So 2 things, a way of inquiring, a body of knowledge. Third thing, science is a particular domain of knowledge. It's not all of human knowledge. Science won't tell you whether Macbeth or Midsummer Night's Dream is a better or more effective Shakespeare play. That's the arts, literature, dramaturgy. So there are other domains of human knowledge that science doesn't tell us much about. Science tells us about the natural world and its behavior, its regularities, and so on. We have psychology for understanding individual human minds. We have sociology for understanding groups of people and how groups interact. So there are these other big bodies of human knowledge, although I just realized that my psychology colleagues would tell me that psychology is part of science, which it is. But we have these other bodies and domains of human knowledge as well. And one of those is religious knowledge, knowledge about faith and rituals and the information about religion and so on. And science doesn't really tell us anything about that divine supernatural element, whether any of that exists, what's going on with that. So science is one subset of human knowledge. It's not all of human knowledge. There's a thing called scientism, which is the belief that the only knowledge that counts is scientific knowledge. And most scientists don't subscribe to that. Most scientists know about a range of other things. Science won't tell me directly whether my wife and children love me or not. there are other kinds of knowledge that are appropriate to judging those kind of things and understanding those kind of things in a deep way. So science is one part of human knowledge. And finally, science is a set of values and commitments. It's a way of looking at the world, and it requires certain ethics. So if you are doing a scientific experiment and the data don't support your position, it's not ethical to throw away the data to protect your position. Science requires a commitment to follow where the data and the evidence lead, rather than to be committed to an existing idea no matter what the evidence says. And that's a scientific worldview, a perspective that values evidence and values finding the answer over ego or over protecting your own assumptions or over a whole variety of other things. So there are ethical dimensions to science as well as the other dimensions. So a set of ways of finding out about knowledge, a bunch of knowledge, the recognition that science is part of but not all of human knowledge, and a commitment to honesty, integrity, ethics in seeking knowledge. I think those are all part really of a proper understanding of what science is. We tend to think about the world and see the world through our concepts. So again, learning science is not just memorizing a bunch of stuff. It's gaining new ways of seeing the world. So a vector is a concept that we use in physics. It's a line that represents something, a force, or something that we can represent that has a direction. And so I learned about vectors in physics, and I've taught about them for many years. And now when I'm walking on a rough surface, I'm kind of seeing little vector lines in my mind of where the forces are so that I won't slip or fall or trip, because I can now judge where the vectors are. So I'm suddenly seeing the world in a different way. I'm able to make these judgments about the direction of forces and the strength of forces because I have this way of seeing the world. But I've done a lot of physics. I haven't done much biology. So what I haven't done is learned about trees. To me, when I drive along on trees, past trees, I might see a palm tree and a pine tree and a gum tree, and that's about all I've got. To me, the rest of it's kind of undifferentiated green stuff. That's a tree, and that's as much as I've got. A biology friend will be able to tell you a Latin name and how it grows, the kind of seeds that it has, the life cycle, a whole bunch of stuff about the tree that is really interesting, but that I just don't know because I don't have that way of knowing the world. And an Aboriginal person is going to be able to tell you not only some of those things about the tree, probably not the Latin name, but probably things about the life cycle, how the life cycle of that tree ties in with the life cycles of other living things in that ecosystem, the spiritual significance of totems and dreaming stories around that tree, that particular thing, and a whole variety of other kinds of ways of seeing the world as well. So each of us have these different ways of seeing the world, and by teaching students science, what we're trying to do is expand their repertoire of ways of seeing the world. So we use this metaphor of lenses. In fact, I've talked in the past about learning as gaining new lenses to look through, not as just gaining coins. We sometimes think about school as kind of gaining coins. You go to school, you collect up all these coins towards getting a career or a job later, and then you can spend the coins later. So this idea that, when am I ever going to use this, miss? Oh, you'll use this in the future to do whatever. The benefit of this sort of lenses perspective on learning is that it means you can use it right now. And you will, and hopefully you'll remember it more if you're using it, if it comes to be the way you see the world. If you get used to thinking about weather maps, for example. We usually see weather maps on the weather on the TV news. But if you kind of know what a cold front is and what a warm front is and what it means that the pressure is dropping or the pressure is rising and so on, then you'll actually start to look at the clouds or look at the sunshine or look at the potential rain in a slightly different way. You'll understand more about what's going on in the world and why it's going on. So it's new, different ways to see what's happening in the world. And we can kind of use them strategically in the sense that I won't always want to use the scientific lens. So if I see a rainbow after a rainstorm, sometimes I will want to think to myself about refraction of light and the way the light is bouncing between the sun and the droplets of water in the air and my eyes to make this continuum of colored lines of light of different wavelengths. But sometimes I'll just want to think more poetically about how beautiful it is, about how cool it is. I might want to think about leprechauns and pots of gold at the end of the rainbow, or I might want to think about my lesbian, gay, transgender, intersex friends and the rainbow flag. We have a range of different ways that we think about the world, and it doesn't mean we have to use the scientific lens all the time, but it's really nice to have that in our little lens kit so that we can access the world that way. The history of science is kind of how we learn about how science is now, is how we learn from the way that it's developed over history. So there are stories about the way in which science has developed over time. And very often, if I'm teaching a concept, I'll also tell a story about the people who were involved. So I might talk about Democritus, the Greek philosopher, and his idea of cutting something in half and then in half and then in half and then in half. Can we keep doing that forever, or do we get to a point when we can't? I might talk about Archimedes figuring out as he got in the bath and the bath overflowed that he could work out the density of the king's crown. About Isaac Newton and the apple falling and seeing the apple. Now, some of those stories might not really have happened, but those are the people who did really exciting things in the history of science. And if I can connect that history with their context, what they were learning, what we learned from them and what we know now, that's engaging for students. And it means that they understand it, recognize it, and can kind of bring it back to mind. So the history of science is really important. Neil Stephenson, the science fiction writer, wrote a trilogy of books called the Baroque Trilogy, which talk about Isaac Newton and Hooke and Huygens and all of the scientists in the 16th and 17th centuries who were looking at science during a time when science was really growing. But he also talks about the growth of money and banking and capital and the growth of empires and a whole variety of other things. They're fantastic books. They're really well worth reading. They're quite thick, but if you're a Game of Thrones or Wheel of Time or Mistborn type reader, they're worth a read because they'll give you some sense of the history of science and where it came from. The philosophy of science is kind of the evidence for it is the history of science. So we look at what scientists have done and then try to philosophize about why they did it and regularities and things we notice. So we talk about scientific revolutions, and I'll talk a little bit more about Thomas Kuhn later on. And the concept of scientific revolutions comes from Kuhn, but we kind of all know something about scientific revolutions. So the idea that the solar system all orbited the Earth, so geocentrism, was an idea that was very popular around about the time of Galileo, that the Earth was at the center of the solar system, and depending on who you ask, the center of the universe, and everything else revolved around the Earth. And then Copernicus and Tycho Brahe and Galileo came along and said, no, the solar system revolves around the sun. And that makes the maths a lot easier and it makes a lot more sense and it works. So there was a scientific revolution. There was a switch. Most people believed that the Earth was at the center. And then after, not instantly, but after maybe a generation, most people believed that the sun was at the center. So there's a revolution from one perspective to the other. And the history of science can be understood as the history of different scientific revolutions, of new ways of seeing the world arriving and then persuading people to accept them and believe them. So that's one way of looking at the history of science. The history of science has tended, certainly when I was growing up, I'm in my mid-50s now, when I was growing up, it was very much about old white guys, initially in powdered wigs, like Newton and those guys, and then in lab coats. And it was mostly guys who look a bit like me, old white guys. Clearly, that's not the full history of science. Women were very involved in the history of science, and we'll talk about a couple of those shortly. There was a very big tradition in the Middle East of chemistry that very much influenced Western chemistry. There were the kind of indigenous knowledges that I was talking about earlier about the Aboriginal person and their understanding of the tree and the ecosystem and the scale of time across the year and so on. There are these various ways. India and China were both very influential in discovering things early that came to the West. So it's clearly a global history and it's a human history. It's not just this kind of very Western European narrow history that we need to understand, and having a better sense of it. I guess the last thing I'd say about the history of science is that we sometimes have this kind of glorious narrative of we were really dumb, we got smarter and smarter and smarter and smarter forever, and we keep getting smarter. It was a simple, linear, straightforward story of progress and growth. Now, it wasn't that. It has been actually much more complicated than that. We've made mistakes. We've gone off in weird directions. So Democritus, who I mentioned before, came up with the idea of the atom in ancient Greece. And then Aristotle, also in ancient Greece, came up with the idea of the four elements, earth, air, fire, and water. And that convinced more people. So we forgot about atoms for a couple of thousand years until Dalton, because Aristotle's idea became more powerful. So we had ideas that we'd had and kind of lost track of and then came back to. So here's a couple of examples of interesting kind of false paths in the history of science. Phlogiston is a great one. So phlogiston, people wanted to be able to account for the fact that if you burn something, if you take a piece of wood and burn it, or if you take a piece of iron and leave it out in the rain so it rusts, or if you take almost anything, some coal and burn it, that you start out with this kind of hard, solid, shiny thing. And over time, it burns down to ash, this kind of powdery stuff, and you get some smoke and so on. Now, Aristotle's ideas actually explain that pretty well. Aristotle said everything is made out of earth, air, fire, and water. So if I take a piece of wood, it's got some of those things in it. When I burn it, I let the fire out because the fire comes up. The smoke comes out, so that's the air escaping, and I'm left with some earth. I'm left with the ashes that look like dirt. So you can see that idea, although we don't hold to Aristotle's theory of the four elements now, it's actually really quite powerful for understanding and explaining what's going on. And there are lots of things where if you take some iron ore and get some of the air out of it, then you're left with more of the iron, more of the earth, more of the hard material that you actually want. And so, it worked quite well. So phlogiston was an early theory about why things burn. And it was there's this substance in them called phlogiston. And when you ignite something, the phlogiston escapes, and that's combustion, and that's why things burn. And you can't burn the ashes again because the phlogiston's already gone. So it's a good theory, it kind of works. But once we actually started doing careful experiments, and Dalton was particularly influential in this, Lavoisier in France as well, they would capture the smoke, they'd capture everything that happened. And in fact, instead of having less mass, because you'd expect that if the phlogiston was there and then it was gone, you'd have less mass at the end. But if you capture everything, the smoke, the ashes, everything from the fire, you actually discover that there's more mass. It's heavier than it was before you started. And so for a little while, the phlogiston theory held on with the idea that it had negative mass. So when you get rid of the phlogiston, you gain some mass, but that's not very satisfying to us. And so eventually we discovered that there is oxygen in the air and that burning is combining with that oxygen in the air. So now we know that if you want to put a fire out, you have to keep the oxygen away from it so it can't continue to burn. And most of our fire extinguishers and fire blankets and all of those things are about keeping the oxygen away so it won't burn. So nobody talks about phlogiston theory anymore, except in this kind of talk about the history of science and false paths, because it isn't as strong as our theory, our current theory, which is that burning is combining with oxygen from the atmosphere. The luminiferous ether, I won't go into in a great deal of detail, but there was this concept that every kind of wave we know about requires something to travel through. Water waves travel in the water, sound waves travel in the air, the waves in the string of the guitar travel in the material of the string and so on. So every kind of wave we know about travels in something. So we thought, well, light waves must need something to travel in as well. So all throughout the universe, even out in space where there's no air or anything, there must be this thing called the luminiferous ether for light to travel through. But later on we discovered, and again I can't get into the maths because it gets very complicated very quickly, but Maxwell's equations, which showed us that light is made up of electric and magnetic fields, and they don't need a material to travel through. They can just travel through empty space. So we no longer believe that there's a luminiferous ether. Luminiferous just means light carrying, because light doesn't need something to carry it. The other thing is that various people's stories were obscured. So Lise Meitner was a German physicist. She did end up being recognized and I believe got a Nobel Prize for physics. But in the early years of studying quantum, Otto Hahn was the male scientist whose name was on most of the papers and so on. And Lise Meitner was doing a lot of the work in the background and conceptually very important. But it took a little while for her work to be recognized simply because she was female in a male-dominated industry. Same in biology with the discovery of DNA and the double helix. Crick and Watson, two male scientists, essentially took the credit, but Rosalind Franklin, the female scientist, had done much of the work. Crick and Watson, I believe, did get the Nobel Prize and Rosalind Franklin didn't. But she's been very much recognized since, but it was one of those stories where initially the public story of what was happening in the science didn't reflect what was actually being done. Marie Curie is an interesting story because there's a movie called Radioactive coming out shortly, which is a life story of Marie Curie. So you may want to check that out when it becomes available. Marie was Polish. Her maiden name was Sklodowska, but she went to France and married Pierre Curie. And Marie and Pierre were both working on early radioactivity, isolating radium and radioactive elements. And they were working together, but Pierre actually went out into the street and got hit by a carriage and died relatively young. And Marie carried on the work. And so she had a number more years to continue with the work than Pierre. So in a sense, her name became much more famous than his through essentially maybe that historical accident, or at least we would have known of them as a couple rather than knowing more about Marie, which I think we mostly do. So just kind of, you can see why stories from the history of science are helpful at getting at ideas about all those elements of science. So the interaction of science with society, for example, and a whole variety of those issues. Okay, getting a little bit philosophical now. So in logic, in the philosophy of logic, to do induction means that you look at lots and lots of cases of something and then create a general law out of that. So if you look at, what's a good example? If you look at lots of men, all the men, let's say in Australia for ease of convenience, and then you look at all the women, then you can inductively say that the average height of the men is slightly bigger than the average height of the women. That doesn't mean that every man is taller than every woman. Clearly that's nonsense, but it means that on average, Australian men are taller than Australian women. That's an inductive law because there's no, in that case, you haven't actually figured out why. You haven't done any genetic studies or any hormone studies or any sort of physiological study to figure out the reasons. All you've done is measure everybody's height and average them all up, right? So induction is go look at lots of examples, and out of those you'll spot similarities and regularities and rules that you can pull together to create a rule. And so you can't say every man will be taller than every woman, but you can say on average men are taller than women. So deduction is the reverse. It's taking a general rule and understanding what's going to happen in a particular case based on that particular rule. So there's a rule in science which says that if you keep the amount of gas you've got the same and decrease the volume, the pressure will increase. So that's a rule, and it means that anytime I have a particular amount of gas and try to compress it smaller, the pressure inside the container will get bigger. So that's deduction. I know the general rule and I know a specific example. So if I squash my motorbike tire to get smaller, the pressure inside is going to get bigger. And that rule will apply everywhere because it's a general rule. The first theory in the philosophy of science comes from Francis Bacon back in the 1600s. And this was the idea that if you observe the world carefully and come to understand the world and these regularities, you can build up a picture that is true of the world. So inductivism is the idea of using induction to build it up. If you haven't seen it, it's not for the faint-hearted. It is kind of gory and kind of sexy and kind of strange. If you haven't seen it though, the movie The Name of the Rose with Sean Connery and Matthew Broderick, Sean Connery is playing a character who is quite like Francis Bacon. That is, he's an early scientist in a monastery among a number of people who aren't scientists, who have a range of various superstitious beliefs about demons and possession and strangeness that's going on in the monastery. And he's applying a scientific eye to that. So The Name of the Rose, from the novel by Umberto Eco, is well worth a look for a sense of what this inductivist approach looks like. So Bacon was very influential. So there's one example that was given, and I think maybe it even arises from Bacon, if not certainly from other philosophers of science, an inductive rule. If you go to Europe and you look at a swan and another swan, you go around multiple countries and multiple areas, you go all over Europe, you look at all swans and all swans are white. So from that, you can inductively deduce, that's not right, inductively induce that the rule, all swans are white. So anytime you find a bird that is a swan, so it can't be a duck or a goose or a falcon or a whatever, it must be a swan, but if it's a swan, it will be white in Europe. So that's an inductively derived law. Lots of experiments, lots of experiences brought together into one law. Now, what it shows though, is that that's a local law. And what we're trying for in science are universal laws that cover the whole universe. And so when scientists came to Australia and encountered black swans, that experiment refuted the idea that all swans are white. There are clearly black swans, and they are swans. They have all the other characteristics of swans, except that they're black instead of white. So that's not a valid rule. And that's the problem with inductivism, is that you can't conduct an infinite number of experiments, and you can't conduct experiments everywhere in the universe. So if your idea is that you can do enough observations to get the truth, you can never do enough observations. That's the problem. There's always potentially that Australia country lurking on the other side of the world where the swans are black. There's always potentially that experiment that refutes your theory lurking somewhere. So you can't make these generalizable rules. There's another problem, and this is a bit of a brain twister, but the other problem with induction is, how do you know that it works? How do you know that it works to make lots of observations and pull them together? The only way you know that that works is by doing it. But by doing that, you are using the law of induction to prove that the law of induction works. And that's kind of logically circular. You can't kind of lift yourself by your own bootlaces. You can't say, I will prove that this is correct, and the only way that I can prove that it's correct is by using the thing that I'm trying to prove. It doesn't really work logically. Now that might be the kind of consideration that doesn't bother you too much, but it did bother philosophers of science quite a bit. So there were various attempts to find a better approach than inductivism, and that's what we'll talk about. So there is that. I just talked about the contents of this slide, so it's just a very long sentence or two that says what I just said, that the problem of induction is that you have to derive, or you have to arrive at it using induction already, and it's circular reasoning. So Sir Karl Popper was one prominent critic of inductivism who he claimed that he'd solved it, but he actually sidestepped it and said, well, let's just not go there. Let's not try and create things by inductivism at all. What we'll do is take a theory, create a theory, and then test it against the world with experiment. If the experiments disprove it or falsify it, then we'll discard it. So if we take the all swans are white theory, we test it everywhere in Europe, it keeps working. We test it in Australia, it fails. Okay, we get rid of the all swans are white theory. So Popper's idea was falsification. Theories are created, we can't prove them. So in science, still, basically ode to Popper, we don't say something is proved. You'll see it in advertising and various other things when they're trying to sell you something. But scientists who are being careful won't say something is scientifically proved or scientifically proven. They will say it's supported by the best available evidence. That's a recognition of the fact that more evidence might be available later that will disprove it. Things can be disproved, so it's kind of not symmetrical. You can't prove it, but you can disprove it. So, the idea that all swans are white has been disproved. There are black swans. It's just not correct. So it can be disproved. It can't be proved, but a theory can be supported by the best available evidence that we've got so far. Thomas Kuhn talked a slightly different way. Remember, I mentioned him in relation to scientific revolutions, going from Earth-centered to sun-centered. That's a scientific revolution. And he used the language paradigms. So a paradigm is a set of theories and ways of thinking. So he would say Earth-centered was a paradigm. It was a way of thinking that made sense of a lot of things. It allowed you to understand why the sun comes up every day, why the moon orbits the Earth and has particular patterns, and so on. And it sort of allows you to understand how the other planets move. It gets very complicated mathematically very quickly to understand the motion of the other planets. But it's a paradigm that kind of works, but it was overcome and replaced by the better sun-centered paradigm. So he talks about a paradigm shift, and that language has moved into our general language. So we talk about a paradigm shift quite often these days. And that's really all owed to Kuhn. And Kuhn talked about switching from one paradigm to a different and better paradigm. And he talked about that process and how it works. So those two really are the big modern philosophers of science. They're the ones that probably everyone should really know about who wants to teach science or be involved with science, because they are incredibly influential. Two other theorists who I think are really interesting. I'm actually going to go backwards on this slide. So Lakatos first. Imre Lakatos was a student of Sir Karl Popper. So he looked at Popper's theory and said, well, that's a little bit too harsh. If just one little tiny experiment can make you throw out your whole theory, that seems too tough, and not many theories would survive that. So he talked about this idea that there's the hardcore, there's the bit of the theory that you absolutely have to have, or it's not that theory anymore. There's the absolute key bit, and then there's a protective belt around it of related theories. And if you falsify any of those edge bits, it doesn't matter, because you can get rid of the edge bit, but you keep the hard core. It's only if the hard core gets falsified, you have to throw away the whole research program. So Lakatos is kind of like Kuhn, like Popper, but with a slightly different perspective that, it's a little bit tougher to falsify and throw away something. The other interesting thing Lakatos said is that a research program can look as though it's in trouble for a while, but then new evidence will come along that will support it, and it will suddenly be resurgent and gaining money, gaining interest, and so on again. So at the time of Newton and Huygens, there was a debate about whether light was a particle or a wave. And then Young's double slit experiment seemed to conclusively demonstrate that light was a wave. And so for a couple of hundred years, everybody thought light was a wave, nobody thought light was a particle. And then we get to Einstein early in the 20th century. And in trying to explain a particular thing called the photoelectric effect, he comes back to the idea that light behaves like a particle. And so now we think that light sometimes behaves like a wave and sometimes like a particle. So the research program, light is a particle, had gone away for a couple of hundred years and then came back only 100 years or so ago now. So this is one of the things Lakatos says, you don't throw it away forever. It doesn't go to the garbage dump. It might go away for a while and then it might come back a bit. And then Paul Feyerabend, who is my absolute favorite philosopher of science, says, look, if you go look at the history and philosophy of science, you go look at what scientists have actually done in the past, no theory is big enough to contain it. People do a wide range of very different things. We often look only at physics, but there's chemistry, there's biology, there's astronomy, and there's geology, and there's a whole bunch of science. and sometimes the rules you make for physics don't work for the others. And so Feyerabend said, look, anything goes. We don't know. It's impossible to create a theory big enough and powerful enough to fully understand the nature of science. So it's an attractive perspective, and he's a very funny and interesting writer. But in the end, it doesn't leave us anywhere useful to go for science education. So I tend to stick with Popper and Lakatos in terms of thinking about the nature of science for science teaching. Okay, so that's probably the dose of philosophy that we've got in this little chat. Now a little bit on scientific methods. When we teach, I certainly go out and see teachers teaching in schools, and they often say the scientific method, and right up on the board, the scientific method. But it's better to talk about scientific methods. As I said, there are many different sciences, and biology is quite different in a number of ways to physics, for example. The methods that are used, the tools and so on, and biology now in the 21st century is quite different from biology in earlier centuries, because we have a lot more access to the genome, for example. The human genome was only fully sequenced quite recently, so there is a lot of information that happens and changes, and having an idea of the one true scientific method doesn't capture the full richness and complexity of what science does. So scientific methods essentially are the things that scientists do, and to some extent they're still inductive in the sense that we go out and do lots of experiments and try to create laws from them. Or verificationism is kind of the flip of that. Verification is the opposite of falsification. So if I've got an idea, what Popper says I should be doing is trying to test it to destruction. I should be trying to falsify it. But often what I'm trying to do as a scientist really is to verify it, to find evidence that supports my idea. Now, if I find evidence that doesn't support it, that ethical stance says I should get rid of it if the evidence doesn't support it. But the everyday operation of science, and Kuhn talked a little bit about science during a revolution versus kind of everyday ongoing science. We generally are supporting our theories with evidence, or testing our theories with evidence. There's a better way to say it. So what we notionally are doing is trying to find ourselves to be wrong. Because if we find out that we're wrong, then we've found a way that doesn't work, and we can go on looking for ways that do work. So I'm recording this at the end of 2020, during the COVID pandemic. There was a story in the paper about a lot of money wasted testing a whole variety of treatments for COVID that didn't work. But that's not wasted at all, because now we know that those things don't work. How dumb would you feel if you got 3 years into the pandemic and everything was terrible and it turned out that cough syrup would have fixed it? You need to know what doesn't work to be able to find what does work. So that's part of the work of science, is finding out the things that don't work. So here's a kind of broad statement of scientific methods. This is how scientists generally proceed. So read the literature, find out what we already know. There is that body of knowledge. There is a bunch of stuff we already know that might come right up to the edge of your question, but don't yet answer your question. And then propose a hypothesis, or an hypothesis, depending on how you work with your Greek language. Propose your hypothesis, determine what you would need to do to verify or falsify. So if the experiment comes out with the blue liquid, it supports my theory. If it comes out with the red liquid, it doesn't support my theory, right? What does the evidence look like that supports your theory, and what does the evidence that falsifies your theory look like? You need to know that to be able to do the experiment, and then gather the evidence. There'll be a independent variable, which will be the thing that you're changing. There'll be a dependent variable, which will be the thing that you're measuring, and you'll keep everything else the same. That will be your controlled variables. So you will gather the evidence in this careful way. I've kind of slid back and forth between the words experience and experiment. And experience is what we do when we go out into the world and just live. Experiment is a special class of experience where we're very careful about controlling the other variables. And some variables make a difference and some variables don't. If I'm doing a chemistry experiment, the temperature probably does make a difference. The color of my shirt or lab coat probably doesn't make a difference. So there are some variables you need to control, other variables you probably don't. But an experiment is this special class of experience where we're careful about the variables. And then analyze the data. So you've got the data, you've made the measurements, you have observed the red or the blue liquid. That's a very simple and dumb example, but you've counted or measured, or your Geiger counter has counted a certain number of clicks, or whatever your particular set of data is. Does it support the hypothesis or not? And then report your result and critically evaluate your methods and actions. So part of what you're doing when you're writing up a lab report is saying, and this is how I know that I can trust my results, because these are the ways I was careful. And also, this is a limitation. I didn't control for color of lab coat. No, that's a silly one. I wasn't able to control for atmospheric pressure, and I think atmospheric pressure might have been relevant. So you critique your own methods to make sure that they're as good as they can be. And if you have an inconclusive experiment, that suggests ways to improve it. So this is an approach you can talk through with students, this process, and it can be as formal or informal as you like. My own children got used to, if they would ask me a question, I wouldn't tell them the answer. I would say, that's an empirical question. We can do an experiment that will tell us the answer to that. Let's go do the experiment. And that's kind of what you're doing as a science teacher, particularly in primary, but really throughout, is saying, well, we can find out. Let's find out together. Rather than, it's much less exciting if I simply tell you the answer. So wrapping up, I guess, the language that we use in science education now kind of relates to Popper's view, this idea of falsification. Theories are things that humans create. There are such things as scientific facts, and a fact is something like, if I let go of this clicker, it will fall at about 9.8 meters per second as long as I'm close to the Earth. That's a fact in science. And then there's a theory, there's a number of theories that explain that. Aristotle has a theory. His theory is everything has its natural place in the universe, and the natural place of most things is on the floor. So if you take it out of its natural place, it wants to get back. So if you let it go, it will go back to its natural place on the floor. That's a theory of gravity. That's a theory of why things fall. Newton had the theory when he saw the apple fall and when he saw the moon orbit, that talked about the ways in which two objects that have mass are attracted to each other. So this clicker has some mass and the Earth has some mass, and they're attracted to each other. That's Newton's theory to explain the facts about gravity. And then Einstein had a theory, which is quite complicated, about how space and matter curve each other, and the curvature of space means that matter moves in certain ways in space. General relativity, that's Einstein's theory. So there are different theories that explain the same facts, because under all those theories, this will still fall and it will still fall at the same speed. So there are scientific facts and there are scientific theories. Theory doesn't turn into a fact. A fact is not just a theory that has been supported by lots of evidence. They're different kinds of thing. We test the theories using evidence from our experiments, and we can falsify them, but we can't prove them to be true. And in fact, Einstein was a big follower of Popper. He read a lot of philosophy of science as well as doing his physics. And he said it very succinctly. Einstein said, no amount of experiments can ever prove me right. A single experiment can at any time prove me wrong. And that's a perfect statement in one sentence of this idea of the philosophy of science. You can never be proved correct. You can be supported by all the available evidence. And it turns out that Einstein is supported by all the available evidence. He was amazing. He made predictions in 1905 and 1915, so over 100 years ago now, that are still being supported, verified by new evidence that's coming in. And every piece of evidence that comes in supports his theories so far. But there are problems with his theories, and that's where the next Einstein comes along and solves those for us. So this has been a relatively long chat and a relatively deep one, I imagine, but hopefully an interesting one, and hopefully one that gives you, if you intend to teach someone science, doesn't mean you have to be a teacher. You can be a parent, you can be a scout leader, you can be someone who works with young people or people who don't understand science. Heck, you can be a child who needs to teach your parents some science about whether they should wear a mask or something like that. If you intend to teach someone some science, then knowing about this stuff, I hope and I think, will be helpful. Thanks very much. See ya.